Bam! Mr. Taru, in this algebra lesson, we are going to be taking a very thorough look at the standard form of a linear equation. In this lesson, we are going to be defining what standard form is. We're going to be taking two algebraic equations and converting them into standard form. The first one, as you can see here, will be starting off in slope-intercept form. Our second example is going to be given to us in point-slope form, and again, we're going to convert those into standard form. Now your point-slope form, your slope-intercept form, and your standard form, these all have, we learn all these forms of a line because they each have their strengths and weaknesses. If I want to graph a line, I certainly want to do that in slope-intercept form. If I'm given information about a line, then I'm going to want to come up with the equation of that line from the given information. Starting off, we're using the point-slope form. And in word problems, sometimes they're best to, as you're trying to convert the words into an equation, you'll kind of more naturally flow into the standard form of a line, and indeed you'll see that in our third example, where we're going to read a word problem scenario, set up a linear equation for it, and then find answer some questions based off of that real life, that word problem setting. We're going to, therefore, roll into this natural idea of finding x and y intercepts when the equation of our line is in standard form. We will do that one more time, because the word problem will involve that a little bit as well. We'll do that one more time with an equation that's not applied to a word problem. We are going to be given the x and y intercepts of a line, and from that information, come up with the equation of a line in standard form. And then finally, we're going to be given this general equation of a line in standard form and convert that into slope-intercept so that we can see if we're given an equation of a line in standard form, maybe we could just look at that equation and determine what the slope is without converting it into slope-intercept form if you, for some reason, would want to do that. So there's a lot of examples in this video, and so thank you for selecting it. I'm sure you might have seen the time that this lesson is and might get a little bit nervous. You will find links to all my examples in the description of the video if you'd like to skip ahead. Standard form of a linear equation, well, we're looking at ax. Let me pause and try and get rid of that static. Let's see if my second channel is any better. We have standard form of a linear equation. Ax plus by is equal to c, where a, b, and c are real numbers, and a and b are not both 0. Now, I've seen this definition in some of my textbooks I have as references, and I've seen this online. However, many textbooks are not going to use this same definition for standard form. It'll still say ax plus by equals c, but they give different conditions on what the coefficients of a, b, and c are. And indeed, I have seen this sort of, these conditions for a, b, and c. I haven't really seen that very often. What I normally see is something like this, where when you have an equation in standard form, a, b, and c, they must be integers, and the coefficient of the x term, which is generally labeled as a, will need to be positive, just even more restrictions on those coefficients and your constant. This is by far the most common that I remember seeing. A and b, they both can't be equal to 0, because if both a and b are equal to 0, you're not even going to have an equation of a line. Also, when you have your equation written in standard form, it should be reduced as much as possible. You do need to have your coefficients of a, b, and your constant of c. They're not allowed to be fractions. They need to be, in the most common definition, integers, which means no fractions, no decimals. And it really should be as reduced as much as possible. Like, say, if a, b, and c are all even numbers, you should divide both sides of that equation by 2 so that a, b, and c don't have any common factors. Think of it as your equation in sort of a reduced form. Our first example of converting just a given equation of a line into standard form is we want to convert y is equal to -3/4 x plus 2 into standard form. Okay, well, this is slope-intercept form. Y is equal to mx plus b. Awesome for graphing. That's the only form I would graph a linear equation from, or a line from. But if we want to get that into standard form, the x and y terms both need to be on the same side of the equal sign. Generally, that's the left, and your constant is on the right. So On the right-hand side of our equal sign, if you would like to see that sort of division between the left and right-hand side, we have a negative 3/4. Well, that's a minus or a negative value, and if I want to move that over the equal sign from the right to the left-hand side, the next term, I need to apply the inverse math operation. A lot of times I say opposite, but really it's an inverse math operation. And the inverse of subtraction is addition. So we're going to add 3/4 x to both sides of my equation, and we get 3/4 x. Now there's nothing in front of this y term. If you don't see any coefficients written, you can assume that that is equal to 1. And if it helps you to have that coefficient of 1 written there, by all means, go ahead and do that. And just for practice, I will do that as well. So 3/4 x plus 1y is equal to 2. So now we have, on the left side of our equation, the x and y term together, and the constant of 2 off to the right. Now, if the conditions of a, b, and c are that a, b, and c are real numbers, you know, I can consider this in standard form, but again, I have not seen many textbooks that have that loose of a definition or conditions for a, b, and c. I'm used to saying that a, b, and c, they all need to be integers and a needs to be positive. Well, our 3/4 is already positive. I just need to get rid of that fraction. Fractions, of course, mean division. It is a division bar. So if I want to get rid of this division of 4, I'm going to multiply both sides of my equation, because multiplication is the inverse math operation to division. I'm going to multiply both sides of my equation by 4. And when we do that, you know, this is going to be finished very, very quickly. We have 4. My 4 is just written as an integer or just a number, if you will, and I'm applying it to a fraction. If you would like to make sure that you keep your numerators and denominators lined up, you might find it helpful to write that as 4/1. Now, if you're really comfortable with your fractions, you'll know that this is going to reduce down to be 4. If you're not, you might do 4 times 3 is 12, over 1 times 4 is 4, x, and then 4 times 1y is going to be 4y, and then 4 times 2 is 8. Now, the whole point of multiplying both sides of this equation by 4 was to get rid of that fraction and get my a, b, and c coefficients and constants, my a, b, c terms. It's not really correct to say call them terms, but to get rid of the fractions. So why did I do that? Well, 12 divided by 4, of course, that does cancel out, or that does reduce down to a value of 3. And I could have seen that right from the beginning and understand that my multiplication of 4 and my division of 4 are going to cancel. But 12 divided by 4, again, is going to be 3x plus 4y is equal to 8. So let's now take a pause, clear off our board, and get on to our next couple of examples. And for our second example, now we're starting with an equation that is in point slope form. Y minus y sub 1 is equal to m times x minus x sub 1. Great form. If I give you a couple of points and ask you for the equation of a line, you have to find the slope first. Now, let's see. How about with this one? We can take the 2/3 and distribute it through the parentheses, and you know, this is just going to be 2/3 x, and then 2 times 7 is 14 over 3. Or you can get rid of the fraction right from the beginning. And I don't necessarily really think one way is that much better than the other, but let's go ahead and get rid of that division of 3. So we're going to wrap the right-hand side of our equation with a set of brackets and multiply that by 3 to cancel out the division of 3. Might want to put that over 1 so the numerators and denominators line up, and then do the same on the left. Now when you do that, don't forget that terms are separated by addition and subtraction. So on the left we have a minus sign, so there's 2 terms on the left. On the right-hand side of the equal sign, we have a plus sign. So you might think that there's 2 terms on the right. But around the x plus 7 is a set of parentheses. That's holding that together like a vice grip, and that is going to act as a single term. So the 2/3 parentheses, I don't care what is inside, is just one big term. Over here, get a minus, no parentheses. Well, I guess there is now a bracket, but inside that bracket, for the purposes of this, before we went to say multiply both sides by 3, there were 2 terms on the left and only one large term on the right. Now, why do I bring that up? Because when you distribute the 3, we're going to have 3 times y and 3 times negative 3. So we have 3 times 1 is 3, and 3 times negative 3 is negative 9. When you go to distribute that on the right-hand side, a lot of students will make the mistake of taking that 3 over 1 and putting it maybe to all 3 of these pieces, 2/3 x and 7, or they'll certainly make the mistake of multiplying it twice because, again, that plus sign between the x and the 7. But that multiplication is, if I pick the right color, only needs to occur, it's incorrect if it doesn't, once. So we're going to have 2 times 3 is 6, over 3 times 1, which is 3, and 6 over 3 is equal to 2. So we have 2 parentheses x plus 7. Now we haven't gotten rid of any parentheses, but we did get rid of our fraction, our division of 3. And that's good for when, I'm looking over here like I still have my conditions. It's good for when we're trying to finish our problem and get this into standard form if we're not allowed to have fractions in our final answer. With a, b, and c need to be integers. We're going to then take the 2 and distribute it through the parentheses, and we get 3y minus 9 is equal to 2 times 1 is 2x, and 2 times 7 is 14. Remember, with that standard form, it's ax plus by equals c. So on the right-hand side, we're only allowed to have a constant, just a sort of naked number, if you will. We're going to, therefore, add both sides by 9. Some of you might want to do 2 steps at once, and I guess if you label your work really, really neatly, that would be okay. For teaching purposes, I am not going to do 2 steps at once. Negative 9 plus 9 is 0, and of course that's going to be 23. Now on the right hand side, to cancel out that subtraction of 9 on the left, we added both sides by 9, that inverse math operation. We have a positive 2x on the left, so we're going to move that over with subtraction. These are not like terms, so please don't do 3 minus 2 is 1. We're going to get negative 2x plus 3y equals 23. And I think some textbooks would be okay with that being considered in standard form, but a lot of books, and I really do prefer to keep it this way as well, a lot of textbooks will not be happy if your coefficient of a is negative. So we're going to fix that negative 2 by multiplying both sides of the equation by negative 1. And negative 1 times negative 2 is positive 2x, and actually just all these signs are going to change. And that is our equation in standard form. And when we started off with point slope form. Now over here, you buy kids tickets for $3 a piece and adult tickets for $5 a piece, maybe just at a small fair. And in total you spend $90. Now, there's adult and kids tickets in a lot of places. Movie theaters, theme parks, fairs, even airlines. So this is maybe a very simple problem, and 3 and 5 may think those are too cheap, but it's a problem, it's a realistic problem. And I want to write an equation to model this scenario, so that we can relate the number, if we have spent kids tickets, bought kids tickets, which were $3 a piece, and adult tickets, which were $5, if we spent a total of $90, what's the combination? That's what this equation is going to do. It's going to relate the kids and adult tickets together along with the $90 total, and from that we can see what different combinations of kids and adult tickets come out to that total price of $90. And so I want to write a model, an equation to model this scenario. Well, how do you figure out your total bill? You're going to figure out how much money you spent on the kids, take the amount of money you spent on the adults. You're going to add those two values together to come up with $90 total that we're given in the problem. Well, how much did you spend on the kids? Well, if they're $3 a piece and no kids go, you didn't spend any money on kids. If one kid went, you spent $3. If two kids came along with the family, well, that was $3 for the first kid and $3 for the second kid, and so that would be 3 times 2 is equal to 6. You're going to pay $3 for every additional kid that comes with you. Well, repeated addition is multiplication. So the way that you're going to figure out how much money you spent on the kids, I was going to erase the label, but I don't need to, I have room. The amount of money you spent on the kids is $3 times how much money you spent on the kids. So I can put X, or I can just write maybe K for the number of kids, and then plus the adult tickets are $5 a piece, so that's $5, and how many times are you going to have to pay $5? Well, that's going to depend on how many adults went. So it's going to be 5A, and that is equal to 90. Most equations we deal with are going to have variables of x and y because of the Cartesian plane, the x-axis and the y-axis, the horizontal and vertical axis. But when you're dealing with word problems, really, your labels can be anything. Just the horizontal, the domain axis, the independent variable axis, the x-axis just has to have a label that matches your particular equation, and same with the y-axis, the dependent axis, the range axis. And so we have our equation in standard form of 5k plus 5a equals 90. How many kids' tickets could you buy? Well, the fewest amount of kid tickets you could buy is probably 0. I don't know, well, I made up the problem. This ends with a 0, so we can divide by 5 evenly. So potentially you could buy no kids' tickets. If $5, if this were, say, $4 and it did not divide evenly into 90, then maybe saying you could not buy any kids' tickets would not mathematically work, but potentially that could be the case. So how many kids' tickets could you buy? What's the maximum number of kids' tickets you could buy? Now, I did make this problem to come out to be as easy as possible. So if we have 3k plus 5 times 0, I could spend all of my money on the tickets for the kids, and that is equal to 90. We do have 3k is equal to 90, because 5 times 0 is just, 5 times 0 adults is no money spent on adults. And to get that 3 away from the k, we're going to undo that multiplication with division and come up with k is equal to 90 divided by 3 is equal to 30. And this is just a early in algebra lesson. You'll have problems that sound similar to this, but will require 2 equations to solve because you'll have a systems of equations. Maybe if I gave you information about how many tickets were bought and the total money spent, that type of problem would require, well, potentially, most people would set those problems up using 2 equations, not just the one here that we have, because again, we're early in our algebra studies and these problems they will become more complicated as you move your way through mathematics. Now I got a few more parts to this particular problem, so let me clear off the right hand side of the board. Our third part of this example, well, we now know how many maximum number of kid tickets we could buy. What is the maximum number of adult tickets that we could buy? Well, let's see. I could spend all my money on adults and not have any kids come, potentially, as long as it divides out evenly with the $90. So we have our equation again of, well, each kid ticket is $3, so we have 3k plus 5a is equal to 90, and if we don't have any kids going with us, we have 3 times 0 plus 5a is equal to $90, That, of course, is going to be 0, and we have 5a is equal to 90. To cancel out that division of 5, we're going to cancel out that multiplication of 5, we're going to divide both sides of our equation by 5, and a is equal to, how many 5s go into 9? 5, 10. Just one. And if you take 5 out of 9, that leaves you with 4. Now we have a 40, and 40 divided by 5 is equal to 8. So we can have a maximum of 30 kids attending if 0 adults show up, and if we don't have any kids coming with us, we can buy a maximum of 18 adults. Now, don't know if there's a clear independent and response or domain and range or explanatory and response. I'm trying to think of all the different vocabulary we use to label the x and y axis when it's not just x and y in this particular situation. But if I go ahead and run the number of kids tickets along the x-axis, then when there was 0 adults, when I plugged in 0 for A, I got a k value of 30. And when we went ahead and tried to find the maximum number of adult tickets by allowing the number of kids to be 0, that came out to be an even number. Thus, we are still satisfying the idea that we spent $90. We got 18, and that's somewhere between 15 and 20. So right there, connecting the dots, and we get a line that looks something like this. Okay, now it's not really a line because saying line is indicating that this would go on forever, and it's not exactly straight either. But this is a word problem, this is an application problem, and it would not be possible for us to have a negative number of kids showing up or a negative number of adults. So let's call it a line segment. And you know what? I just sort of inadvertently went over how you can take an equation in standard form and graph that line using x and y intercepts. Any point along the x-axis, like if I were to ask you, and you could respond through the camera, what is the coordinate of that point? You would say, well, from 0, 0, I moved the origin, I moved to the right 5. So it's 5, 0, 10, 0, 15, 0, 20, 0. When you are crossing the x-axis, you have a y-coordinate which is equal to 0. And when you're on the y-axis, like from the origin 0, 0, just simply moving up 5, that's 0, 5, 0, 10, 0, 15, 0, 20, and 0, 18. So just by setting up this word problem, we naturally flowed into the standard form just because of the nature of the way it's written. And we kind of just started our introduction to x and y intercepts. So let's go ahead and get that formal, like how do you find an x and y intercept, even though I verbally said it, and do one non-application problem where I give you an equation, we find those x and y intercepts, and then we're going to be given x and y intercepts and try and find the equation of a line. Bam! Last scene. We're going to find an x-intercept by letting y equals 0. We talked about y in the previous screen. We're going to find a y-intercept by letting x equal 0. So we're going to find the x and y-intercepts of the line 4x minus 5y is equal to 40. And again, I did kind of set this up so it would work out rather nicely. And now I'm standing in the way. We're going to find an x-intercept by letting, again, y equals 0. So we're just going to substitute that in. We have 4x minus 5 times 0, because we're trying to find an x-intercept, so we're letting y equal 0, is equal to 40. Well, of course, anything divided by times 0 is going to be equal to 0, so that's going to cancel out. We have 4x is equal to 40. Dividing both sides by 4 to cancel out the multiplication of 4, we get x is equal to 10. Now, to find a y-intercept, you just repeat the same process, only this time you let I say y-intercept, we're going to let x equal 0. Oh, yes, excuse me. Now this x equals 10. This is already labeled as an x-intercept. Make sure you give your teacher the answer in the form that they like. They might be perfectly happy with x is equal to 10. They might also want to see that as a coordinate of a point, and so you would want to write that as 10, 0. If we're letting or finding a y-intercept, we're going to be letting x equal 0, and maybe I should do this in a different color to separate the two. For a y-intercept, we're going to say that we have 4 times 0 minus 5y, that looks like a 4 a little bit, let's clear that up, is equal to foote. Again, anything times 0 is 0, and that might be a big deal when you're multiplying, but adding by 0 is the additive value for addition, so that's just going to cancel out. We have negative 5y is equal to 40. We're trying to solve for that y, trying to find that y-intercept. We're going to undo that multiplication of 5 by dividing by 5, negative 5, and we get y is equal to negative 8. So our y-intercept is negative 8, or since we let the x equal 0, 0 comma negative 8. Now we're going to find the x and y intercepts and write the equation of this line, which I didn't draw. So let's see, just to match my notes, we have got an x-intercept of 3, y-intercept of 3, sorry about that. And then 1, 2, 3, 4, 5, we have an x-intercept of 5. Of course, we're not going to know that without having some labels on our graph. And we're looking at this line right there. So, what are the x and y intercepts of this line? Well, I can just look at the graph. Where is this line crossing the y-axis? Let's do that first. Y-axis, right there. So our y-intercept is equal to 3. Now, I do like to have my kids write, I wouldn't be totally happy if they just wrote y equals 3, even though it's not technically wrong. I like them to say, okay, the y-intercept is equal to 3 and have their labels very clear, and our x-intercept is going to be equal to 5. Now, it also says here, and let's pick a different color. What have I not used yet? I've used green here, but we want the equation of the line, and we want that in standard form. Now, I have lots of lessons on finding equations of lines. I'll put links to those in the description of our video, but when you have a picture, you can see everything that you need to write the equation of a line, not in standard form, but in slope-intercept form. Well, slope-intercept form is y is equal to mx plus b. Now, y, I don't normally like to use this form when given information about a line and trying to write, a final answer for the equation of that line. I prefer using point-slope form. But when you're looking at a graph, this is the slope and the y-intercept b. I can look at the graph and identify both of these. This yellow line, we've already said, is crossing the y-axis at 3. So we have y is equal to, now I haven't identified the slope yet, but we do have x plus 3. What is the slope of this line? Well, you don't necessarily have to, but I do like reading graphs like a book, left to right, at least if you're reading English and many other languages, but not all of them. So I do like to read graphs left to right. I do like my rise over run, my slope, my rise over run, change in y over change in x. I do like that run value to always be to the right. And when you have a picture, all you have to do is identify a couple of clear points and look for that rise over run movement within the graph. Well, I gave us the points. So I said we labeled some x and y intercepts. So to get from this point on the left towards or to this point sort of more to the right in the graph, we're going to go down. Hopefully this red is showing up in the camera. Going down 3 and over 5. Well, when you move down, that's a negative movement on the y-axis. So that's negative 3 and a run of 1, 2, 3, 4, 5. So our slope is negative 3/5. Now, I'm going to finish that in white, just make sure it's all legible. I want this to be in standard form. Well, this has a fraction in it, and I don't like to have my values of a, b, and c be fractions. I want them to be integers, because I'm used to my textbooks having that condition on the equations of lines in standard form. So to cancel out that division of 5, I'm going to multiply both sides by 5. 2 terms on the right, so make sure you distribute that to both of the terms on the right when you apply that multiplication of 5. And we get 5y is equal to, now this time, because we're getting close to the end and I've done one of these examples, the multiplication of 5 and the division of 5 are going to cancel, leaving us with this negative 3x plus, don't forget to just write 3, or don't just write 3, but don't forget to multiply. 5 times 3 is equal to 15. I do have on the right-hand side of my equation still my x term. In standard form, it's ax plus by and then equals c. The constant needs to be alone, so this negative 3x on the right-hand side needs to come over. And I'm going to bring that over with addition, only because of space I'm just going to write my answer. I'm going to add 3x to both sides of my equation and have a final answer of positive 3x plus 5y. These are not like terms. This has an x and that has a y, so don't put them together and write 8y or something like that. And that is equal to 15, and this is the equation of that line in standard form. Now to finish up our video, our lesson, what is the slope of a line in standard form? I'm not sure if it's really that important to memorize this, but if you know it, if it's in the back of your pocket or in the, in the back of your mind, you can just pull out when necessary. Standard form, ax plus by is equal to c. Plus, some textbooks like to ask this question. Sorry about the hammering outside. My wife is working out there. When you look at an equation in standard form, you can look at that value, that coefficient of x, and just go, whoa, we have a negative 3/5 in front of the x, so the slope has to be negative 3/5. It's much more complicated to look at the equation of a line in standard form and do that as well, because the y value just isn't alone. But I can solve this for y, and then if I keep that slope, that coefficient in front of the x just in the back of my mind, maybe that can help me save some time with some later problems. So we're going to subtract both sides by ax. And that is going to give us, chalk down! That is going to give us by is equal to negative ax. Well, actually, I don't really know what a is, so the opposite of ax, plus c. And then we are going to get rid of that coefficient of b by dividing the entire equation, or both sides of the equation, by b. Now, I am out of room, but I don't want to just skip showing that last division step, so we're going to have by is equal to negative ax plus c, and we're going to divide both sides by b. And our final answer, the b's cancel out. We get y is equal to negative a over b x plus c over b. Well, that, at least in general terms, is the equation of our line in slope-intercept form. Y is equal to I'm starting to read it, mx plus b. Now, I'm not using the same letters as what we see in the equation because I'm just trying to verbalize that slope-intercept form for you, but point is, we can, with the y term alone, just look in front of the x and see that the slope, when looking at an equation of a line in standard form, if I do the opposite of a over b, just pulling the numbers out of this equation and going, oh, well, a is, 2 and b is equal to 3. Well, then the slope of that line is going to be negative 2/3, and that is the end of my lesson. I hope this clarifies any questions you might have had with equations in standard form. I'm Mr. Taru. Bam! Go! Go do your homework.